So in this video, I'm going to be talking about resistors in series and parallel. And all I'm going to be doing is deriving the formulas for when you have a couple of resistors in series and some in parallel. So let's say that we have a voltage source here, and we have a couple of resistors, and it's going to ground. This value is arbitrary. So you have R1, R2, and R3. So straight away, what you can notice is that the current going through the resistors is the exact same. So I'm going to write that out. And the whole purpose of this experiment is to simplify this down to like an equivalent resistance. So I'm going to write that out here. I'm going to call this resistor Req to represent the equivalent resistance. And V1 is the exact same here. And one thing you're going to notice is that since this is just the equivalent version of this circuit, the current going through the circuit is the exact same. So all I'm going to do is write Ohm's law for both scenarios, and you're going to see that you can solve for the equivalent resistance. So in this scenario, you have the following. So you have V1, and then you have 3 voltage drops because of the polarity of the resistors and the way the current is going. So you have V1 minus I R1 minus I R2 minus I R3 equals 0. So that's your KVL loop for the left side. And I'm going to do the same for the right side. So V1 plus minus here minus I REQ equals 0. So the next thing I'm going to do is I'm going to collect the terms with I here and then move them over to one side. So V1 equals I R1 plus I R2 plus I R3. And I'm going to factor out the I. So V1 equals I times R1 plus R2 plus R3. And I'm going to do the same thing to this side. I'm going to move the I over to this side. So V1 equals I REQ. And so one thing you're going to notice about this is that V1 is the same in both scenarios, and so is I. So what I can do is I can actually set these two equations equal to each other. So I can write I times R1 plus R2 plus R3 that equals I times REQ. And so as you can see, the I is the same in both scenarios, so you can just cancel that out. So you get that REQ equals R1 plus R2 plus R3 plus R3. And so all this result shows you is that when you have a bunch of series resistors, meaning that the current going through each resistor is the exact same, you can simplify them to one resistor that's just the sum of all of the resistors. And this is just in the case where you have 3 resistors. I'll actually simplify this to when you have multiple resistors. So let's say that this goes on forever. So I'm going to do dot, dot, dot. And I'm going to say this is R sub n, n representing any integer. So REQ for this circuit is going to be R1 plus R2 plus R3 all the way to Rn. So the next thing I'm going to be doing is showing you how to simplify a bunch of resistors that are in parallel. So what I'm going to be doing next is showing you how to simplify a bunch of resistors in parallel. So remember, parallel means that the voltage across the components is the exact same. As you can see across R1, R2, and R3, the voltage is just V. And you can tell that because they're connected to the same 2 nodes. They're all connected at the top at this node and at the bottom at this node. I'm actually going to label this ground node. And I'm going to simplify this circuit on the left to this circuit on the right. So I just combined R1, R2, and R3 to this REQ. And as you can tell, it's got the same current going through it, or the same current source being applied, and the same voltage across it, as you can see here. And so what I'm going to do is I'm just going to write KCL at this top node right here, and I'm going to do the same for this circuit, and we're going to see if stuff equals each other or anything cancels out. And so since this is my ground node and V is being applied across all three of these, I can tell that this top node is at a voltage of V because this plus is right here, this minus is right here. So the voltage across has to be V. And so I'm just going to write KCL at the top node. So I have one current going in, which is just I from the current source. And that equals all the currents going out, which would be I1, I2, and I3. And what I'm going to do is I'm actually going to label the pluses and minuses on R1, R2, and R3 to represent the voltage drops as the current passes through it. So plus minus here, plus minus here, plus minus here. And if you remember from Ohm's law, V equals IR, I is the current going through the resistor, R is a resistance itself, and V is the voltage difference across the resistor. And so I'm going to use this, I'm going to simplify this to I equals V divided by R. I'm going to use this relationship to replace I1, I2, and I3 in this circuit. And so if you examine I1, the voltage across this resistor is V. So that means that I1 is just going to be equal to V divided by R1. Because V, again, is the voltage across this resistor. So I2 is going to be the same V, but it's divided by R2 this time. And finally, I3 is going to be the same exact V. This time it's divided by R3. So this is as much as I can simplify for now. All I'm going to do is repeat this process with the circuit on the right. So in this case, I have one current going in. The voltage at this top node is still V because voltage applied across here is V. And I have one current going out. And as you can see, it's just I because there's no current going through here. This is just me showing you what the voltage across the resistor is. So in that case, I can just write Ohm's law directly by saying I equals V divided by REQ. And so the I in these two scenarios is the exact same because that's the independent current source that I've placed here. So I can set these two equations equal to one another. So V divided by R1 plus V divided by R2 plus V divided by R3 is equal to V divided by REQ. And in this case, every single V value is the exact same because that's what I have. That's the voltage across every single one of these components. Again, because they're connected to the same two nodes. If they're connected to the same two nodes, that means that the components have the same voltage across them. And so I'm going to cancel out the V, and I'm left with this equation. So 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over REQ. And if I want to rewrite this, this means that REQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3 inverse because I just took the reciprocal of both sides. So this is your final equation for this specific circuit. And so just like with the series resistors, I'm going to generalize this. So I'm going to erase this. So if I have this general circuit here with a bunch of resistors in parallel, I can simplify this to this particular circuit. I is the same here. Where REQ is equal to 1 over R1 plus 1 over R2 all the way to 1 over Rn inverse. So this is your general equation for combining a bunch of resistors in parallel. Thank you.